At this point in the course, we will take a break to discuss two ways to multiply vectors. The dot product of two vectors, which plays a major role in work and energy, and the cross product of two vectors, which will play a major role down the line in rotation. In our early videos, we already saw a third form of vector multiplication, scaling. In scaling, a vector is multiplied by a scalar, a quantity with no direction. Scaling either changes the size of a vector or flips its direction. It can be done in either polar or rectangular coordinates. Now, let's look at the dot product. A dot product can be interpreted as a measure of how well two vectors align with each other. Unlike scaling, which multiplies a vector by a scalar to produce another vector, a dot product takes two vectors and multiplies them to produce a scalar. As its name suggests, a dot product is symbolized by a dot. If we have two vectors, A and B, their dot product would be called A dot B. Dot products can be taken in either rectangular or polar. Obviously, both calculations will give you the same answer, so your choice of whether to use polar or rectangular depends only on whether you were given the vectors in polar or rectangular originally. Let's start with rectangular. Suppose you're given this question. You have two vectors. The first is 3i hat plus 4j hat. The second is 8i hat plus 6j hat. What is their dot product? The vector drawn in red is the vector 3i hat plus 4j hat. The vector drawn in purple is the vector 8i hat plus 6j hat. And we've been asked to find the dot product. Now, since we have these two vectors in Cartesian coordinates, in rectangular coordinates, let us see how you would solve for the dot product in rectangular. So the first vector has the coordinates 3i hat plus 4j hat, as we said, and the second one has the coordinates 8i hat plus 6j hat. To calculate the dot product when your vectors have been given in Cartesian, the process is like this. Take the x coordinates for each of the two vectors and multiply them. So that would be 3 multiplied by 8. Then take the y coordinates and multiply those. That would be 4 times 6. And then add together the two products. 3 times 8 is 24, plus 4 times 6 is also 24, so the dot product of these two vectors is 48. In general, we can say this. Suppose you have two vectors in rectangular. The first has coordinates ci hat plus dj hat. The second has coordinates ei hat plus fj hat. The dot product is found by multiplying the x coordinates, c times e, then multiplying the y coordinates, d times f, and then adding those products together to yield a single number with no direction. Now, let's see how to do it in polar. I will use the same vectors I used in the previous example, but translate it into polar notation to show that you get the same answer. You have two vectors. The first is 5 oriented at 53.1 degrees, and the second is 10 oriented at 36.9 degrees. What is their dot product? The vector 3, 4 in polar would be written as 5 at an angle of 53.1 degrees, whereas the vector that is written as 8i hat plus 6j hat in polar would be written as 10 at an angle of 36.9 degrees. So now let's take a look at how we would solve for the dot product of these two in polar. In polar, the rule is you take the length of the first vector, in this case, let's say that's 5, multiply it by the length of the second vector, that would be 10, and then multiply by the cosine of the angle between these two vectors. So the difference between these two vectors would be 53.1 degrees minus 36.9 degrees. 53.1 minus 36.9, that gives us 16.2 degrees. So now this whole thing multiplies to 5 times 10 times the cosine of 16.2 degrees. So what is the cosine of 16.2 degrees? It's 0.96. So this now works out to 5 times 10 times 0.96. 5 times 10 times 0.96 gives us 48. To summarize, to find the dot product of two vectors A and B in polar, you take the size of A, multiply it by the size of B, and then multiply that by the cosine of the angle between them, symbolized by the Greek letter phi. Again, this produces a scalar, a single number with no direction. While I showed both rectangular and polar for the sake of completeness, in this class the polar form will be far more common. Consider this example. You have two vectors. The first is 11.2 oriented at 60 degrees, and the second is 4.5 oriented at 150 degrees. What is their dot product? Here are our two vectors. The first with a length of 11.2 and an angle of orientation of 60 degrees, and the other with a length of 4.5 at an angle of orientation of 150 degrees. Now, given this information, let us solve for what the dot product would be. We'll use our familiar approach. Take the length of the first vector, that's 11.2, multiplied by the length of the second vector, that's 4.5, and multiply by the cosine of the angle between them. That would be 150 minus 60. So this follows from the vector symbology that we've been using so far. That is, that dot product is calculated as length of the first multiplied by length of the second multiplied by the cosine of the angle between them. So here the length of the first would of course be 11.2, length of the second 4.5, angle between them is 150 minus 60. So let's simplify this a little bit. 11.2 times 4.5 times the cosine of 150 minus 60 is 90. So now let's solve this out. What is the cosine of 90 degrees? 0. So that means that this entire expression simplifies down to 11.2 times 4.5 times the cosine of 90, but that's 0, which means the whole dot product is also 0. In general, whenever you have two vectors that are pointed 90 degrees apart from each other, like this, the dot product will always be 0, because you're taking the cosine of 90 degrees, the angle between them, and the cosine of 90 degrees is 0. If two vectors are 90 degrees apart, the dot product always works out to 0. This fact will be important when we start applying the dot product calculation to work. How about this example? You have two vectors. The first is 6.7 oriented at 26.6 degrees. The second is 6.7 oriented at 153.44 degrees. What is their dot product? Now, let's take a look at this circumstance. Here, we have one vector with a length of 6.7 units at an angle of 26.6 degrees, and a second vector also of 6.7 units, but this time at an angle of 153.44 degrees. We're going to find the dot product of these two vectors. And since these vectors have been given in polar, we will use the usual polar way of solving. It works out to A times B times the cosine of the angle between them, which we call phi, or phi, if you want to be absolutely accurate about it. So the size of the first vector is 6.7. The size of the second vector is also 6.7, multiplied by the cosine of 153.44, or the angle between these two is measured as 153.44 minus 26.6 degrees. So let us solve this out. 153.44 minus 26.6 gives us 126.84. So we have 6.7 times 6.7 times the cosine of 126.84 degrees. Cosine of this quantity is negative 0.599, about negative 0.6. So now we have 6.7 times 6.7 times negative 0.6. So what does that work out to? 6.7 times 6.7 times this answer is negative 26.9. So what we observe here is that we have now gotten a negative dot product. A negative dot product results whenever the angle between the two vectors is more than 90 degrees, because the cosine of anything more than 90 degrees is going to be negative. And that's precisely what we observe over here. To sum up, if two vectors are more than 90 degrees apart, the dot product will be negative. As we've seen, if they're exactly 90 degrees apart, the dot product is 0. And if they're less than 90 degrees apart, the dot product is positive. Now we're ready to explore the cross product. While scaling multiplied a vector by a scalar to produce another vector, and the dot product multiplied two vectors to produce a scalar, the cross product multiplies two vectors to produce yet another vector. Not only that, the vector has to point at 90 degrees to the original two vectors. We'll only see how to solve cross products in polar. They can be solved in rectangular, but you need linear algebra to do so. The polar method is far simpler. As you probably guessed, the cross product operation is symbolized by a cross. We read this expression as A cross B. Let's try an example. You have two vectors. The first is 7.1 oriented at 45 degrees. The second is 7.2 oriented at 146.3 degrees. What is their cross product? Here we see two vectors. 7.1, or a first vector with a length of 7.1 at an orientation of 45 degrees, and a second vector with a length of 7.2 at an orientation of 146.3 degrees. We want to find the cross product of these two vectors. Now, a cross product is going to produce yet another vector. So that means that we need to find both the magnitude, that is the size, and the direction of that second vector. First, let's find the size of this second vector. The size of the second vector is like this. Take the size of your first vector, multiply it by the size of the second vector, and then multiply that by the sine of the angle between them. Now, this is a bit different from what we saw before. When we were dealing with cross products, with dot products, it was similar, but we had a cosine here. Cross products use sine. Dot product use cosine. So let us substitute everything in and let us solve. So the length of the first one, 7.1. The length of the second one, 7.2, times the sine of the angle between them. That's the angle between them is given as the difference of these two angles. That's 146.3 minus 45. So let us solve for this. 146.3 minus 45 gives us 101.3. The sine of 101.3 is 0.98. So this is all going to become 7.1 times 7.2 times the sine of 101.3, which, as we just calculated, was 0.98. So when we calculate that cross product, it works out to 7.1 times 7.2 times 0.98, which is 50.13. So this is the size of the cross product, but we still have to find the direction. The direction is found using something called the right-hand rule. And the right-hand rule goes something like this. Take your right hand, keep it straight, and line it up with the first vector, like this. Then curl your fingers so they point in the same direction as the second vector, like what I'm doing right now. Then extend your thumb. Your thumb will point in the direction of the product vector. So in this case, my thumb is pointing out of the sheet of paper, outwards, upwards from this paper if you prefer. Whenever you have two vectors, the cross product must always point at 90 degrees to both of them. And the only way that can happen in this case where you have two vectors that are in the plane is either for the cross product to point out of the page or into the page. In this particular instance, the cross product is pointed out of the page, and we know that because of the right-hand rule. The cross product always points in the same direction as your thumb. The way that we would symbolize that is to attach to this 50.13 the letter K hat to symbolize the fact that this is in the positive z direction. A positive z direction is called k hat, whereas a negative z direction would be called negative k hat. So this is our cross product. 50.13 k hat. It is a vector 50.13 units in size, which is pointed out of the plane like this, in the positive z direction. The general process is like this. If you have two vectors in polar, A and B, the cross product creates another vector. The size of the product is found by taking the size of A, multiplying by the size of B, then multiplying by the sine of the angle between them. Not the cosine as we did for dot product. For cross product, it's the sine. The direction is given by the right-hand rule. Now, let's repeat that last example, but with one subtle change. The vectors will be in the opposite order. Let's see what effect this has. You have two vectors. The first is 7.2 oriented at 146.3 degrees. The second is 7.1 oriented at 45 degrees. What is their cross product? Now what we're going to do is we're going to reverse the order in which we did the cross product. So we'll do the 7.2 vector first and the 7.1 vector second. So that means that using the definition of the cross product here, the 7.2 goes first, the 7.1 goes second, and once again we would take the angle between these two, so that's going to be the same sine of 101.3 degrees. Now this is exactly the same product as what we had before, so when we solve it out, I'll just mark it down as being reversed over here. When we solve it out, we're going to get 7.2 times 7.1 times 0.98, which is going to work out to 50.13 again. So the size has not changed when we flipped around the order of the vectors. But let's take a look at the direction. To find the direction, we start by taking our right hand, aligning it with the first vector, in this case that's the 7.2, and curling our fingers to point in the same direction as the 7.1. This is the only way you can do that. And now when you extend your thumb, it points into the page, downwards, the negative z direction, or the negative k direction if you like. So correctly, when I assign a direction to this quantity over here, I would write it as negative 50.13 k hat. So this is something you have to be very careful about when you're doing cross product calculations. The order of the cross product is going to alter the result. If you do it in one way, you're going to get a positive value, and if you do it the other way, you're going to get a negative value. So one will point out of the board, the other will point into the board. So you have to be very careful which order you do it in. You can't swap around the order. This effect is unique to cross products. In cross products, order matters. If the order of the original vectors is reversed, the cross product changes direction. So it's very important to keep track of which order the original vectors were in. Finally, what if the two vectors are pointed in the same direction? Consider this case. You have two vectors. The first is 9.1 oriented at 45 degrees. The second is 10.2 oriented at 45 degrees. What is their cross product? That would be solved by A, B
times the sine of the angle between them. So, easy enough. A is 10.2, B is 9.1, times the sine of the angle between them. But they're both at 45 degrees. So that's going to work out to the sine of 45 degrees minus the sine of 45 degrees, which is 10.2 times 9.1 times the sine of 0 degrees. Whip out your calculator and solve for that. The sine of 0 degrees is 0. So that means that this product will turn into 10.2 times 9.1 times 0, which is, of course, 0.
When the two vectors point in the same direction, the cross product is 0. This video discussed dot and cross products. We will use these as we move on to work and ultimately rotation.